Good morning and happy new week. This morning I'm going to talk about distributions. So let's get right into it. Anytime we are dealing with variables, we have to look at how the different levels, how participants are sorted into the different levels of that variable. So for instance, in this case, we have a variable called gender, and we have male and female. So we have 2052 individuals falling within the cell for male and 2170 falling within the cell for female. And if we look at the percentages, this is an SPSS statistical computer package output, and it gives you two different percentages because the percent includes any missing values, but we don't have any missing values in this case. So these two are actually equal. But we have 48.6% of all participants falling within the male and 51.4 within the female category. So that's our distribution. That's what our distribution looks like. So it's basically just telling us how many participants within a sample fall within a given cell, or in this case, a given level of our our variable, right? We use frequencies and percentages when we're dealing with discrete variables to talk about our distribution, and we use bar charts to plot them. So here we have the bar chart for this variable, and we have male and female, and there's slightly more females than males. So this is just a way to plot it. When we are dealing with continuous variables, by contrast, we don't use these frequency distributions because we don't have any discrete values. Instead, what we do is we look at ranges of values, right? What we provide, though, is means and standard deviations, right, to describe our sample. So again, we don't do frequencies and proportions. And for our figure, we provide what are known as histograms. So this is a histogram. You'll notice that I also plotted what's called a normal distribution, and we're going to talk about that shortly to underlie this distribution of values. So you can see that the distribution of blue lines representing some density of individuals does not match the normal distribution quite perfectly. So all probability distribution functions. So now we're talking about functions, right? We talked about functions when we discussed variables, but in order to make a plot, right, of some sort with our distribution, we have a function, right? There's a function underlying this distribution. So each different probability has its own distribution, and there's different kinds of probability distributions for different types of variables. So for instance, we have the bell curve for a normal distribution. So if you look at this figure, you can see the bell curve right here. It looks like a bell, right? That's why it's called the bell curve. Interestingly, virtually all distributions that are not normal, well, when we call the bell curve is a normal distribution. So virtually all distributions that are not normal, there are a few, I think there's a few, right, that don't have finite mean and variance that are not, that this doesn't apply to. They converge to normality, to converge to this nice bell-shaped curve, right, as the sample size approaches infinity after a simple transformation, and that's really key. And this is something known as the central limit theorem. If you're interested in the derivation, if you like math and you like knowing, you like doing proofs, I did a proof for the central limit theorem. You can click this link here, or you can actually just look at my Google, not my Google, my YouTube page. I also have it there. All distributions have what are known as natural parameters. Remember, parameters are to population as statistics are to sample. Here's the ones that we're going to cover today. We're going to cover the Bernoulli, the binomial, the Poisson, and the normal. So for the Bernoulli distribution, its natural parameter is P, the probability. This is the way we write them. We write the name, and then in parentheses, we put the natural parameters. For the binomial distribution, we have N and P, right? N being the sample size, or the number of trials in this case, number of Bernoulli trials, excuse me. Lambda for the Poisson, that's like a rate parameter. And then for normal, we have mu for the mean and sigma. Sometimes you'll have sigma squared for variance, but I just did sigma for the standard deviation. We'll start with the Bernoulli probability mass function. When we're dealing with discrete distributions, we have probability mass functions. When we're dealing with continuous distributions, we have probability density functions. We think about it because you have these specific discrete categories and they have mass, right? So that's, excuse me, probability mass function. So this distribution is just really related to a binary event, for instance, a binary trial or experiment that has two possible outcomes. So that's what's known as a Bernoulli trial, right? And the two possible outcomes are success or failure. Examples of this would be a flip of a coin. Say you want to know, like you call heads, so success would be heads, failure would be tails. Outcome of, say, COVID-19 screening, success would be having COVID, failure would be not having COVID. Again, now remember, you can't take these terms like success and failure qualitatively. You have to just understand that's what we use in statistics. So our probability mass function for the Bernoulli is p to the x times 1 minus p to the 1 minus x, right? So that's the probability mass function. And we add it across the different levels of the random variable. Remember, there's only two different levels here. If we let 1 equal success and 0 equal failure, and x is our variable, like say coin flip, right? That's our variable. The outcome could be 1 for heads for success and 0 for tails for failure. And this sigma, remember, if you'll recall, means to add. So basically we're adding two things, 0 and 1. And this is a really, really nice equation. It's very simple, right? Because if if we have success, we have p to the 1, which is p. Then we have 1 minus p to the 1 minus x. Well, 1 minus 1 would be 0. So anything raised to the power 0 is 1. So we just get px. So that's the contribution for success. For failure, x is equal to 0. P to the 0 is 1. 1 minus p to the 1 minus 0 is 1 minus p. So that's your contribution for failure. Like all probability distributions, and I mentioned this before, they have to, I said the sum of all the probabilities of all the events in the sample space, all possible events in the sample space has to add up to 1, right? So these have to add up to 1. So if we sum this is going to equal 1. So, I mean, that's how we actually prove whether or not an equation actually is the equation for that distribution, the appropriate probability mass function, or is a probability mass function. It has to sum to 1. Here's an example. In Bucks County, Pennsylvania, the probability of being positive for COVID-19 was 0.675 on a specific date. I have more information down here if you're interested. Or 6.7, there was a 6.75% chance of being COVID positive, sometime in 2021, I recall. So if we were to take our equation here, we plug in the value. So P is the probability of success. So the probability of success is 0.675. Okay, so we get that value raised to the x, and then its probability of failure is the complement of that event. It's 1 minus 0.0675. So then we get x is equal to 0, and then we have x is equal to 1. So you have the two, because again, we're adding these together for when x is equal to 0 and when x is equal to 1. Notice when x is equal to 0, the element that remains is 1 minus 0.0675, which gives us this value here, 0.9325. And when x is equal to 1, the only element that remains is 0.0675. So we add those together and they equal 1, like they should. Okay. Again, here's a video showing the derivation of the Bernoulli probability mass function. Looks like this was like sometime during COVID, because I look like I have two chins or something like that. That's my beard. All right, let's talk about the binomial. So the binomial distribution it allows us to predict the probability of a certain number of successes in a given number n of independent Bernoulli trials. So each one is independent of the other. So again, flip of the coin is a Bernoulli trial. And we assume that the probability of success remains the same or constant across all n Bernoulli trials. And here we have, again, so this is the PMF here, and this, we'll have to go over this. And then again, I just show you how we're going to calculate it here by adding them together, by summating them. But the PMF is n choose x, and that's how we read this. This is called the binomial coefficient. And then here, this is basically the same equation we had for the Bernoulli. Actually, if we're only doing one trial, we'd have x equals 0 to 1. And this whole coefficient will reduce to 1, and n is 1. Here, basically, we have the Bernoulli PMF. So now I'll show you how to do all this now. Imagine our goal is to know the probability of 5 COVID-19 positives in 10 independent Bernoulli trials. Since each trial results in only one of two outcomes, success or failure, each trial is a Bernoulli trial. Since we are interested in the probability of 5 successes, we'd use the binomial equation to calculate the probability. The binomial is, like I said before, is a simple extension of the Bernoulli, right? Here's a derivation, a video showing the derivation of the binomial distribution. This is, as I mentioned, is the binomial coefficient. N choose x is like a choose function, if you want to call it that, where n is the number of independent Bernoulli trials, and x is the value we're looking for. Like we want to know how many, we want to know what's the probability of like 5 successes. So this is actually asking you how many ways can we sort 5 n things x at a time, right? So this is translated, like I said, or how many ways can we select, compare, organize n cases x at a time? Excuse me. A little chilly today, and like I get some asthma symptoms whenever it gets cold. So x is the number of successes, and n is the number of Bernoulli trials. So here's our example. Here's an example. If we wanted to know how many ways can we arrange three things 2 at a time, right? Go 3, choose 2. So this exclamation point is 3 factorial. This is divided by 2 factorial times 3 minus 2 factorial. So we get 3 factorial times 2 divided by 2 times 1 factorial. So this is what it would look like, right? 3 times 2 times 1 times 0. 0 factorial is 1. Otherwise, we'd always get 0. So you get 3 times 2 times 1. And in the denominator, we have 2 times 1 times 0. And then we have 1 times 0. Well, that's what it is. I mean, we can do some crossing out too, right? We can cross things out. Like we can cross out 2 times 1 times 0 factorial because we have 2 times 1 times 0 factorial in the denominator, right? We can cross those out. This is a multiplication and division, right? So then we have 3 divided by 1 times 0 factorial. So we get 3. So there are 3 ways to arrange 3 cases 2 at a time. So here's an example of how that would work out. If we have 3 cases, A, B, and C, we can arrange them 2 at a time as A and B, A and C, and B and C, right? So there's 3 different ways to look at these 2 outcomes. So let's go to our example here. What's the probability of identifying 5 COVID-19 cases in 10 independent Bernoulli trials if our probability is 0.0675? So it would be 10, choose 5, right? So using our equation, we plug in the p's here, the probabilities, right? We already did this before for the Bernoulli, but the denominator now, the sum power here is 5, and then it's 10 minus 5. And here we have 10 factorial, 5 factorial, and 5 factorial. Well, so what I do in this case is I'll go 10, 9, 8, 7, 6, and 5, and then I'll stop here at the largest number in the denominator. Well, both are 5, so I just stop at 5 factorial. I can cross one of those out. What I get is this final number here. I carry out the products, and I get 0.000249. Wow, so the probability of identifying 5 cases was, well, if I multiply this by 100, I get 0.0249%. Not very big. What's the probability, excuse me, of identifying 4 or 5 COVID-19 cases in 10 independent Bernoulli trials? Well, we already did the probability of 5, that we just did that now. Let's do the probability of 4, because remember, either or, we can add them together. We learned that in the probability axioms, right? Or the probability of either of two disjoint events can be added together to get the probability of either of the two occurring. So we do the same for 4 cases and we get 0.00287 or 0.287%. So the probability of 4 cases or 5 cases, and I'd mentioned before that the union symbol means or, and it also means addition, so we can add those two together and we get 0.00312. So that's the probability of getting 4 or 5 cases. This is interesting. I want you to really pay attention here. What's the probability of at least one COVID-19 case in 10 independent Bernoulli trials? So at least one, there'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's a lot of different cases, right? So the literal person will add them all together. And so they'd have to do 10 of these right here, right? But since you're so smart taking this class and you already know from what I said before about complements, so I can say, well, wow, okay, what's the complement of at least one case? Well, that would be 0 cases, right? So then all I'd have to do is calculate the probability of 0 cases and then subtract that from 1 and I'd get the probability of at least 1 case. So see, so it's just using what our knowledge of probabilities, we can calculate the probability of 0 cases is 0.497. So the probability of at least 1 case would be 1 minus that, or 0.503. So you can make things simple, right? Make them simple. Poisson. This is actually the first time I've taught Poisson random variables. I feel so lucky. So this is the distribution of the number of events within some unit of measure. Could be time, could be space. So for instance, examples of time would be the number of cars passing through an intersection per hour. Yeah, I should do that because I ride my bicycle all the time and I hit these, especially on weekdays, these busy kind of, I don't know what you call them, like little highways, the bypasses, and man, they get busy. I could just do that count per hour or count per minute or something like that. Or the number of customers entering a clinic per day, right? Or in space could be the number of, the kind of parrot I have is a rainbow lorikeet. The number of rainbow lorikeet parrots landing on a porch in a week, so you can plan how much food to buy. Or the number of lightning strikes hitting a square mile section of forest. Those are all examples of where you'd use a Poisson. So you could do a lot of planning with it. The number of events in a unit of time or space is a discrete random variable. We talked about discrete random variables, including counts, right? So it uses a probability mass function. So the probability mass function for the Poisson is, okay, so this is lambda raised to the x. And x is going to be the variable you're looking for, like what's the probability of 5 cars passing through the intersection, etc. E raised to the negative lambda divided by x factorial. So let's do one, okay? What's the probability of observing 5 cars passing a house in 1 minute if the average number of cars passing my house, or should I house or my house, whatever. Let's do my. I don't think I can. Here it is. My house in 1 minute, if the average number of cars passing my house per minute is 2. So this is my lambda, 2 per minute, right? So I have my lambda and I just plug it into the equation. So it's 2 and we want x is equal to 5, right? So that's our variable here. So lambda 2 to the 5, e to the negative 2, because again, lambda is 2, and then we have 5 factorial in the denominator. So we get 0.036 3.61. So there's like a 3.61% chance that five cars will pass my house in 1 minute. Pretty cool. I threw this one in here. It should be two, not one, but okay, I'll fix that. I threw this one in here because a lot of people give you, a lot of professors give you these kind of questions, right? They're just slightly tricky. But let's read that. What's the probability of observing 7 cars passing a house? I'm gonna do my house. I was trying to be less, I don't know, more general, but I forgot that I need both of them. What's the probability of observing 7 cars passing my house in 5 minutes if the average number of cars passing my house every half hour is 36? You see, what I did here was I I decided to, change the units here to make you think a little bit. Okay, so we have how many 5-minute periods are there in half an hour? There'd be 6, right? Because 6 times 5 is 30, right? So I need to divide this by 6, right? So I'd get 6 per 5-minute period. You see what I did there? Again, let's talk through this. I gave you this is the rate for every half hour, right? But I'm asking you about 5 minutes. I'm not asking you about a half hour. So if you use 36, that would be wrong. So I need to divide this by 6 because 6 times 5 is 30, right? So how many 5-minute periods are there in a half hour? There's 6. There's 6, right? Because 6 times 5 is 30. Or 30 divided by 5 is 6, right? So I get my rate is 6. So my lambda is 6, right? Lambda is 6 per 5-minute period. I did lambda to the x, and x is 7 here, right? Lambda to the x, so 6 to the 7, e to the minus 6 over 7 factorial. I get 0.138, or there's a 13.8% chance that I'd have 7 cars passing my house every 5 minutes. So just be careful of stuff like that. Normal distribution. So the normal distribution, that's the one we already looked at with the bell shape. We talked about its natural parameters are the mean and you could say variance or standard deviation. Just note that this, for your FYI, for your information, the sample mean and sample variance are unbiased estimates of the population mean and variance. So unbiased estimate. So there's a video here. If you're interested, you can click on YouTube and watch the video, how I prove that the sample mean is an unbiased estimate of the population mean. Let's look at this sampling distribution of the mean. We're going to need this shortly, right? As we get into hypothesis testing. But we use samples to estimate our population. So these are our samples right here. These samples are taken from the population. So imagine we collected all possible samples from a population, and the samples have some size n. We'll just say n for now, right? If we were to calculate the mean of all of these sample means, so we take the sample mean for each of these, right? The mean of each of these samples. If we calculated the mean of each of these samples, we'd have the sampling mean. And if we looked at the distribution of those means and took the mean of those means, we'd get the population mean. That's known as the sampling distribution of the mean. The standard deviation of the sampling distribution of the mean is what we call the standard error of the mean. So this is, if you look at it, it says, first of all, it's a standard error of the mean, standard error, and then there's the mean, sampling mean. And it's sigma, that's the population standard deviation divided by the square root of the sample size. So basically all we're doing here is we're weighting it for the sample size. That's all we're doing here. But this is essentially the same thing as looking at the entire, just like looking at the standard deviation of the entire population, but we have to take into account that we have different sample sizes here. That's why we're doing that. This is really important. The further these sample means are from the population mean, the less likely they are to occur by chance alone, or the less likely they are to represent the population. So this is our population. And you'll notice here that it's centered at 0. So this is a standardized population. We haven't really talked about that yet. I think either now or the next lecture. But if we look at the distances, so as we go out, these larger numbers or these smaller numbers, they're further and further away as their absolute values increase. So the further and further away they are from the population mean, the less likely they are to occur. So like sample 4, 1, and 5 are much less likely to occur than samples 3 and 2. So that's something to keep in mind. I want you to remember that. Okay. Also, the standard error of the mean is inversely proportional to the square root of the sample size. Well, we see that right there, but that's going to be important too when we get into hypothesis testing. And we talk about power. You'll see that sample size has a big impact on power. All right, well, why are we doing this now? And why am I holding off on so much information? Well, I don't want to give you too much information now, but we'll talk about this in relation to confidence intervals. So in this lecture, I talk about confidence intervals. So what's a confidence interval? It's an interval in which we believe with some degree of confidence, and we define this, that we'll find the true population mean value. So anytime we estimate something like the sample mean, well, I mean, we estimate the population mean with the sample mean, it's just an estimate. It's one value, right? That's called a point estimate. However, we're not 100% sure that that point estimate is accurate. Even though I said it's an unbiased estimate of the sample mean, we don't know if it is actually equal to the sample mean, right? So what we do is we provide a confidence interval. So we have our estimate. Here in this case, it's mean, right? Remember, it's X with a line over it for sample mean. And then we add and subtract some margin of error, right? And this margin of error we'll calculate using information, including our standard error of the mean. And we'll use this other value, this point here. We'll talk more about that later. But for now, we're just going to call it this point. So it's this point of demarcation in the distribution. And there's a lot that we have to learn about here, and we're going to talk about alpha soon, but not in this lecture. But I'm just going to give you the equation for right now. All right. So our margin of error is some z value. A z value here, when we're talking about a z value in this case, we're talking about a standardized value, some standardized value. So the standardized values are values that we can relate to this population, or we're standardizing it with respect to the population. So we can say how far in these standardized units we are away from the mean in either direction. Like this is 2 standard deviations away from the mean. This is 4 standard deviations away from mean. This is 2 standard deviations below the mean. So that those will have a lot of meaning for us. But in order to create that confidence interval, we have to have these. So first component is this z1 minus alpha over 2. So this z value covers some proportion of all sample values, and it accounts for 1 minus, or covers 1 minus alpha over 2% of all sample values. Alpha represents the probability of a false positive result. So for instance, we reject some hypothesis, but we did it by mistake and we shouldn't have rejected it. Or here something that you might understand better, we conclude the COVID vaccine works, but it doesn't, or you test positive for COVID-19, but you are actually negative. Those are false positive results. Okay, get it? Because you test positive, but you're negative. Researchers select their alpha. So again, we'll talk more about this when we get into hypothesis testing, but researchers selected, and it seems like the most popular value is 0.05, which represents a 5% chance of a false positive result. So to a large degree, the researcher can dictate what is considered an adequate false positive result or an acceptable false positive probability. The complement of alpha is confidence. So 1 minus alpha equals confidence. So these two are complementary, right? And that's why we can use this rule of complementary events, right? So we can calculate confidence just by subtracting alpha because they have to add up to 1. Since the interval surrounds the mean, we split alpha in half. So half of the mean, half is above the mean and half is below the mean. So that's why we split it in half. One thing we know about the the normal distribution is that it is perfectly symmetrical. And because it's perfectly symmetrical, half of all values, 50% of all values are below the mean, and 50% of the values are below the mean. So let's I need to bring up this. So I'm going to pause for 1 second. Let's see how I can pause this recording. Yeah, I had to pause for a second because I need this table for us to complete the work. So this is a table that shows us the area under the curve between 2 points, 0 and whatever our z value is, right? Since the standard normal distribution or the normal distribution is a continuous distribution, we don't really have points of mass. So instead, what we do is we look at the area between 2 different points to get our probability. Like when we were looking at male and female, I say, what's the probability of being male? But I can't do like, what's the probability that someone weighs 182.3654712 pounds, right? I mean, well, I can actually, it's 0, but that doesn't really help me a lot, right? So what we generally do is we look at the probability between 2 different points here. And in this table, the gray area or whatever this color is, represents the area between 0 and whatever a z value is. Okay, so we're going to be working with like these areas on the outside. Now notice that this table only gives you half of the distribution. It doesn't give you the lower half, but we don't need the lower half because everything's symmetrical. So we can just work with 1/2. So let's go back to our lecture here. Okay, so we want to find a z value with a level of confidence. So we're using alpha of 0.05, okay, with the level of confidence. Okay, so let's go here. So z 1 minus alpha over 2. This is cool. I love this. So z 1 minus 0.005 over 2, right? So that's c1 minus, well, 0.05 divided by 2 is 0.025, not 2.25, 0.025. And that is equal to z of 0.975. Okay, so 0.975, what does that mean? So in this table here, 0.975, well, z of everything in this distribution. So we think of now in terms of what's called a cumulative distribution function, right? So in this case, it's everything that goes from negative infinity up to the z value. So we need a z value that covers 97.5% of this table here, right? Of this distribution here, leaving only 2.75% at the other end, right? I think so I said, right? Yes. 2.25, right? 2.5% at the other end, 2.5% at the other end, right? So, and why we pick those specific values, it's really interesting because we're doing that on both sides, right? So it's going to cover 97.5% of all values going from left to right. Then if we flip this over, going from right to left, you'll have this 2.5% of the distribution left open here. And why we're doing everything except for the lower and upper 2.5% is because if we add 2.5 plus 2.5, we get 5%, and we said our probability of a false positive result is 5%. And again, we're going to learn more about what that means specifically when we get into hypothesis testing. But right now, we're just calculating this z value. So we need a z value that's associated with a probability of 97.5%, right? So this is the upper 2.5%. So 1 minus 2.025 is equal to 0.975. So the area to the left would be 0.975, and the remaining 2.5% would be here on the right. Now, let's take a look at our table. Now, our table only covers the area between 0 and that z value, so we have to add 50% here because the table doesn't cover that 50%, right? We have to add 50% here too. So, or in this case, we have to subtract 50% to look at our table. So 0.975 minus 50% is 0.475. So 0.475, right? So we look for a value of 0.475. The areas in the numbers in here represent the area between 0 and some z value. We don't know what that z value is. We know that it has to be around 0.475. And here it is. Actually, here's 0.475 right here. And the value is 1.9. And we read this across 1.90, 1, 2, 3, 4, 5, 6. So 1.96 would be the value. Okay. I hope you understood that. So you might have to listen to this twice. So this table doesn't give you the lower 50%. And we need to find a value that's associated with 0.975. So when we get from 0 to whatever the z value is, we have to subtract 50% to look at this table. 0.975 minus 0.5 is 0.475. And we looked for 0.475 and we found it in the table. And the z value associated with that is 1.96. Because this is hundredths value, 0.6. This gives you the tenths. So there you go. So we go back to our nice little work here, and we get our z value is equal to 1.96. Now the reason I did 1.96 within these brackets here, right? The absolute value is because we're using both positive 1.96 on the right side of that distribution and negative 1.96 on the left, because this interval surrounds our point estimate. All right, okay, let's go ahead and do this then. Okay. So this is this area right here. Okay, see, this is really nice figure here. This shows you the area within. So it's bounded by, so if I go from negative infinity, I stop here, this covers 97.5% of the distribution, right? And the upper 2.5% is what we're interested in right here, right? We're trying to find the cutoff point for that, right? And then since this is symmetrical, we do the same on the other side, right? We set the cut point there. The area between here is our area of confidence. We're 95% confident that all values within here belong to this population, right? For these other 2.5%, here we're not that confident. We're only like 5% confident that they belong to this population. Okay. Here's an example. Do Danielsville high school students weigh more on average than high school students statewide? We are using the Rodriguez weight index instead of weight. All right. The RWI accounts for weight, height, and lean body mass. That's muscle and bone density. RWI scores range from 0 to 100, with higher scores representing greater progression to obesity. Okay. RWI has a population mean of 68 and a standard deviation of 15. So imagine that we collected data on a sample of 100 adolescents and their mean RWI is 70. So we want to do a confidence interval around the 70. We don't do confidence intervals around the population values. We're doing it around our sample value. All right, so step 1, calculate the margin of error. We have the z1 minus alpha over 2. Well, we just did that for alpha of 0.05. If we're looking for a 95% confidence interval, 1 minus 0.95 is 0.05. So that means our alpha is 0.05. So you can remember they're complementary. So we have z1 minus alpha over 2 over sigma over the square root of n. So we have 1.96. We just did that. And we have 15. That's our sample size, right? No, not sample size. Sorry, our standard deviation. Our sample size is 100. We get 1.96 times 1.5, because 15 divided by 10. And we get 2.94. So that's our margin of error. So to calculate our confidence interval, we just use the following equation. It's the mean plus or minus the margin of error. So 70 plus or minus 2.94. So we're plus or minus, we add and subtract from 70, right? So we get 67.08 is the lower limit and 72.94 is the upper limit. So we're 95% confident that the true population value is somewhere between 67.08 and 72.94, right? Or if some people, usually the more accurate translation would be if we took 100 samples from our population, 95% of those 100 would contain the true population mean and the other 5 would not. That's basically what the confidence interval is. That was our first question, right? What was our second question? So do they weigh more on average than the population statewide? Well, we calculated the confidence interval, and using the confidence interval, we can actually answer that question. What we want to see is that our sample, wherever mean is, wherever it is, so it was, I think it was 80, right? It was 80, wasn't it 80? Oh no, it was it was 70, and the population mean was 68. We would want we'd like draw a separate one of these nice bell-shaped curves, and we don't want it to include the true population mean value. So we know the true population mean value is 68. We'd like 95% confidence interval to exclude that true population mean value. Again, here it's translated to 0, right? But the true population mean value is 68. So when we draw up our interval, we look to see if this true population mean value, 68, falls within that interval. If it falls within that interval, right, we are not certain that our sample is different from the population, right? We cannot conclude that our sample weighs more than the population. So if we look at this interval, it's 67.08 to 72.94. Well, 67.08, this interval includes the true population value of 68, right? Because it starts at 67.08, goes all the way up to 72.94, and in its voyage, it crosses through 68. So we cannot really conclude that our sample is different from our population. Okay, here's a couple of practice problems for you to do. I'll do one of them. Well, here, I'll just show you how they're done. And then we can head out. Imagine I collected data on a math competency test from a sample of 40 students. The population mean score on math competency is 78, standard deviation is 9. If one student had a mean competency test score of 80, calculate the 95 of one sample on one student, I'm sorry. Calculate the 95% confidence interval for our sample, and is the sample different? Okay, so let's go ahead and do that. Here I did it by hand. Should be able to see this fine. Again, you're on a computer, so you can do whatever you want, right? So we have mean of 80. What did I say? Let me just make sure I have the right values here. Oh yeah. Okay, so calculate the 95 and then calculate the 90. Okay. All right, so I think I did them backwards. Yeah. So here's the 95%. I did it backwards. All right, so with the 95% confidence interval, we have the mean is 80 plus or minus, we get our equation z1 minus alpha over 2 times the standard error of the mean. 95% confidence interval, again, we're going to be using 1.96. So you can, when we're doing these problems and we're dealing with a normal distribution, we know that the z value associated with an alpha of 0.05 or 95% confidence interval is 1.96. You can just kind of remember that. So we have to do our standard error, which is sigma divided by the square root of n. Our sigma here is 9, and our sample size is 40, so we need the square root of 40. Once we calculate that, we get 80 plus or minus 2.795, and we get our 95% confidence interval to be 77.205 to 82.795. And we know that the population mean was 78, right? So again, we have our lower limit is below 78 and our upper limit is above 78. So we cannot conclude that our sample is different from the population because, again, the confidence limit includes the true population mean value, and we don't want it to include the population mean value. The second question was, is this use the same information but calculate the 90% confidence interval. So 90%, see, now we have to change our alpha, okay, because our alpha cannot be 0.05 because 1 minus 0.9 is 0.10. So we're going to calculate a 90% confidence interval. So we have to find a new z value. So let's go through this step by step. With z 1 minus 0.10 divided by 2. So now this becomes z1 minus 0.05 or z 0.95. So this is going to look at the upper 5% of the distribution, right? The upper 5% of the distribution. So we need a value that corresponds to an area covering an area of 95%, right? Because 1 minus 0.05 is 0.95. But again, our table only gives us the values between the mean of 0 and whatever that z value is. So we subtract 0.5 from here, we get 0.45. So 0.95 minus 0.5 is 0.45. So we need to find a value that's around 0.45. And luckily I found it right here. Look, it's between 0.4495 and 0.4505. It's somewhere between there, right? So we can split the difference. So we get 1.601234.5. So it's somewhere around 1.645, right? Somewhere between that. We would say 1.645, right? So going back to our problem and our figure, here it is. I used 1.645, right, for that z value times your standard error. And then we get 80 plus or minus 2.341. And again, our 90% confidence interval has a lower and an upper limit. And the lower limit is 77.659. And our upper limit is 82.341. So we'd say that while our point estimate of the population mean value is 80, we're 90% certain that the true population mean value falls between 77.659 and 82.341. So is this supposed population with a mean of 80 different from the true population? Well, let's see, our true population mean is 78, and 78 falls within this interval because 77.659 is just below it, 82.341 is above it. So unfortunately, we cannot conclude that our sample differs from the population mean with 90 or with 95% confidence intervals. Let's see, is there anything else we got to do? So there's one more problem here. So is the sample, so this is one with using a 99% confidence interval. So I'm just throwing around different ones so you can work it out. So the population mean score on a stats competency test is 75 with a standard deviation of 8. It's the population values. So it's this is the mu and the sigma. I collected data on a sample of 35 n equals 35 students after completing my course in statistics. If my student's mean score is 81, calculate the 95% confidence interval, and then we'll do the 99. Okay, let's do those here. So let's go to the next page. Okay, 75, 8. Mine were 81. There's 35 students, so the 95% confidence interval. Again, this one is 95%, so you should realize right away that we're going to use the 1.96, right, for the 95% confidence interval. Our mean is 81. After calculating the standard error, we get 1.352. So if we calculate our interval, it's 78.350. And the lower limit, and then 82.650 is the upper limit. And the question was, is our sample different from the population? Are my stats students smarter than the other students after taking my course? Well, yes, indeed they are, because look, our lower limit is 78.350 and the population mean is 78, so we're just above it, right? So our value, our sample represents a different population, right, with a mean of 81. Notice how here this really sloppy drawing of mine, that my distribution of my students is far enough away that a very small percentage of individuals fall below the original population mean value, right? And so we're 95% certain that this is, our true population mean value, and that we could say that we're pretty certain that it's different from the original population, right? Only like 2.5% of our population is below the original population mean value. That's pretty cool. Doing the 99% confidence interval. So we go through the same process again. It's our mean plus or minus a z1 minus alpha over 2. So this time, 1 minus 0.99 is 0.01. So our alpha is 0.01. Divide that by 2, and we get 0.005. So we need to do z1 minus 0.005, and we get z of 0.995. And then we calculated our standard error. We already did that before, so it doesn't change. It's 1.352. All right, so we need to find a z value that's associated with 0.995, and we go in here. And again, we go 0.995 minus 1 minus 0.99. I'm sorry, 0.995 minus 0.5, because again, this represents only the area from 0 to whatever the z we're looking for. So 0.995 minus 0.5 is 0.495. So we need 0.495. So 0.495, somewhere up here. Yeah, somewhere around here. So it's going to be 2.5, 2.50, 1, 2, 3, 4, 5, 6, 7, like 2.57 or 2.58, somewhere like that. And then we're going to multiply that by our standard error, and we'll get our margin of error. And that's what we got here. Right. So I think I should have been 2.575 times that, right? Times that value. I think I forgot to put that little piece in there, right? And then we get our 99% confidence interval is 78.425 to 83.575. Well, actually, you know what? I'm going to just double check to make sure I didn't mess up on something there. I will not give you guys anything that's not correct here. So we said it was 49495. So it's 2.57. 2.575. Is that what I said? 2.50, 2, 3, 4, 5, 6, 7. Yeah, 2.575. All right, so that's good. Let's do this. We're going to get it all right. So we get clear. Oop. 2.575 times, and we had our standard error was 1.352. So times 1.352, and that equals 3.4814. All right, so let's make sure to get this right. So now what we're going to do is take our mean, and we're going to subtract this value from the mean. So let's go. So if you can remember this, 3.481. So 81 minus 3.481 equals 77. See, so I was a little bit off there. Okay, so that wasn't right. 77.519. Okay. And then we go 81 plus 3.841. Well, 81 plus 3.841 is 84.3, 84.481, right? So our value, our confidence interval, our 99% confidence interval ranges from 77.519 to 84.481. And again, we asked, does that include the true population mean value? And the true population mean value here was I guess it was 78. So, well, in this case, no, we're not better. So see this, because I made that error right here. No, so we are not still better. We cannot be confident if we're using a 99% confidence interval that our sample is different from the population, right? Cool. And that mistake was very helpful, actually. So anyway, that's it for today. Thank you very much. Be prepped to do any kind of confidence interval they'll ask you to do. Thank you. Bye.